This is, but I have to have a thesis proposal at 10:30, so let's do that. Let's check this. The thing is, we still have students, and we have students in Australia and Silicon Valley. So you're looking like 20-hour difference, right, between the two lines. And so we are forced to have weekend physics. We have no choice. What spring break in Australia is not spring break in Pittsburgh, is not spring break in Kigali, is not spring break. They're not synchronized, right? So if I begin to make exceptions for all of them, I lose a month. Foundations and idle minds.
Busy after this, could you help me on the part one?
Okay. Morning, everybody. For this final lecture of the semester. Yes. Hooray! Wow. All right. Okay, guys, please shut your laptops one last time. Do we have an attendance poll? Actually, we'll skip the polls for this last class. I do have polls on the slides. I'll just ask you questions. So today's last lecture is going to be on Hopfield nets. I typically also cover Boltzmann machines, but I'll skip that because we don't have time. But then Hopfield nets are a very interesting topic, and they were originally designed as a model of how human cognition works by John Hopfield. And then they kind of fell out of fashion. Boltzmann machines came up from there as a statistical version of Hopfield networks. And here's a very nice paper from 2021. This is on, it's part of the readings. The paper is up on the web page. You can take a look, which literally says Hopfield networks are all you need, which shows that, with a minor modification of the update rule, they actually provide you the attention mechanism used in transformers, and this enables characterization of heads of transformer models. And these heads perform in the first layers, preferably global averaging, and higher layers, partial averaging via metastable states. So what are all of these interesting terms? Now, the models themselves are kind of interesting. What we've seen so far are feed-forward neural networks where stuff goes in and stuff comes out at the other end, and no neuron ever processes a given input twice. But what if the output of a neuron was fed back to the input? So for example, if neuron A fed neuron B, but neuron B went back and fed neuron A. So how would these networks function? So for this, the figure to the bottom, with the outputs going back to the input, that's essentially the same as this network here. We are speaking of loopy networks, where each neuron's output goes to the next neuron, and neurons receive inputs from all the other neurons. Now, for the purpose of illustration, and also because that's how Hopfield nets were originally defined, we're going to assume binary activation. Each neuron compares its input to a threshold, and the outputs are either plus or minus 1, depending on whether the total input weighted, the affine input at the neuron exceeds or falls below the threshold. And for further simplification, although this is not mandatory, I'm going to assume that the weights are symmetric. So the weight with which neuron I connects to neuron J is the same with weight with which neuron J connects to neuron I. And this is what is called a Hopfield network. It's a loopy network where each neuron receives inputs from every other neuron and has a threshold activation. So how would such a network function? Now, at each time, the neuron receives some weighted sum of inputs plus a bias from the other neurons. And if the neuron's output is currently +1, and if the weighted sum of the inputs is also, the affine input term is also +1, positive, then the neuron is not going to change its output. Because the output, basically, the output is simply the sign of the affine value. So if both of these, if the output is currently positive, and the affine value is positive, there's nothing to do. Similarly, if the output is currently negative and the affine value is currently negative, there's nothing to do because both of them match. The neuron changes its output. It flips when the sign of the affine value coming in does not match the sign of the current output. So if the total weighted input that comes in is positive and the neuron is currently negative, it's going to flip to become positive. If the total weighted input is negative and the neuron is currently positive, it's going to flip, right? So we can say, alternately, you can state it like this, that if the product of the current output of the neuron and the affine value, that is at the input of the neuron, is positive, which means both of them are the same sign, the neuron does not do anything. On the other hand, if this product term is negative, meaning the current output and the affine value have different signs, the neuron is going to flip its output. Now, how would this behave? A neuron flips if the weighted sum of other neurons' outputs is of the opposite sign to its own current output value. But when this happens, by flipping its own output, this may cause other neurons to flip. So, for example, if I have something of this kind, let's say the whites are +1s and the blues are -1s, and I have a network of this kind where every neuron is connected to every other neuron, then that top left neuron over here may find that the weighted sum of the affine value, which I will call the field of the neuron, has a sign that's different from its current output. So if that happens, then the neuron's going to flip. It's going to change its value. But then when this neuron changes its value, the field, which is the affine value at the other neurons, will change. And this may cause one of those neurons to flip. And when those neurons flip now, what happens is that the field at this neuron goes right back to, has suddenly changed all over again. And this may cause the first neuron to flip right back. So you can have this kind of behavior. That makes sense to everybody? Right. And so here are 20 evolutions of a loopy network of this kind with random sets of weights. And you can see how, neurons cause other neurons to flip, which may cause the original neuron to flip all over again. These are just 20 evolutions. Here's a bigger animation with 120 evolutions, and you can see how the entire network keeps on flipping, right? So would this kind of evolution continue forever? What does your intuition tell you? Anyone?
Some cases yes, some cases no.
Some cases yes, some cases no. Okay, so let's see how this works, right? Will the behavior continue forever? Now, consider any single neuron. So just before it responds to its input, it has some value y minus. After it responds to its input, it has a value y plus. The neuron always responds by aligning its output to the sign of the field, the affine value at the input. So in other words, when it is done, y and this guy, the field, will have the same sign. Before it is done, these two may or may not have the same sign. So let y plus be the response after it has responded to the input, and y minus be the value before it has responded to the input. This term, we are guaranteed, is positive. If the neuron has not flipped, y minus is the same as y plus, so this term is also positive. Both are in fact identical. This difference is 0. On the other hand, if the neuron has flipped, then we are guaranteed that this term, before the response, the current output and the field were different signs. So this term was negative, this term was positive, right? And the difference between minus of minus is a positive value, right? So the overall, this y plus times field minus y minus times field is simply going to be 2 times y plus times field, because y minus and y plus are basically plus and minus 1 respectively, right? So every flip of a neuron is guaranteed to locally increase the product of the output of the neuron and the field at the neuron. Now, let me define a value d, which is the sum over all neurons of the product of the field of the neuron and the output of the neuron. So now this summation I, y times the field at the neuron, the field by field I refer to the affine value. This guy, if I just expand it out, it is the weighted sum of the products of all pairs of neurons plus whatever comes from the bias term. And every time a neuron flips, this is guaranteed to increase by twice the field at the neuron, twice the magnitude of the field at the neuron, right? So now let's look at this. If everything is positive, if everything is finite, that d value, because all the y's are either plus or minus 1. All the weights are finite, all the biases are finite, so d has a finite magnitude. It has a finite value. Also, the smallest amount by which d changes when a neuron flips is 2 times the field, the lowest, smallest of the fields at any neuron. So if you just look at the difference, each flip of a neuron increments d by a fixed value, a minimum value. D has a cap. So the ratio between the smallest change and the cap is going to be the maximum number of steps that the field can change, right? So in other words, there's a finite number of flips, the finite number of responses before any sequence of flips converges. That making sense to everybody? Okay. Now, so having agreed that this is an interesting process, we're going to come up with a few definitions. These definitions came up from analogies to thermodynamic systems. We won't spend a lot of time on the analogy in this class because we have only one lecture. But let's just define this guy here. See the d? The d was simply the sum over all neurons of the product of the output of the neuron and the field. I'm going to define minus half of this as the energy of the network. Why the minus half? It's a matter of convenience, but also because if you think of how much d increments by anytime a neuron flips, there's a factor of 2. The minus half cancels the factor of 2, so you get nice unit values, right? Okay, so this energy E is minus half of the d term I just described. So d always increases when the network evolves, when any neuron flips. So alternately, you can say this energy E, which is the negation of d, decreases. So the energy of the evolution of the Hopfield network constantly decreases its energy. Now, I have a poll, but we actually don't have polls on Piazza, so you can shut your laptops, guys. Questions? First one, is the first statement true? Yes or no? Can everybody say it out? Yes. Thank you, right? What about the second one? And the third? Would the third be true? What do you think? True. So here is how I can actually see a Hopfield network. Your Hopfield network, there's a chalk here somewhere, I'm sure.
It's over there.
I can think of a simple Hopfield network with, say, 4 neurons. I can draw this like so. So these are the connections, right? So this is one evolution of the Hopfield network. Then the second evolution of the Hopfield network is going to be something of this kind. The only difference is that the weight here is going to be the same as the weight over here. So I can unroll the evolution of the Hopfield network over time and make it one very, very deep MLP. And in the Hopfield network, where it doesn't have to be infinitely deep, the depth is going to be whatever the maximum number of evolutions are allowed by the current set of weights, right? So a Hopfield network is a loopy binary network with symmetric connections. Every neuron attempts to align itself with the signs of the weighted combinations of the outputs of other neurons, which is the local field. Given an initial configuration, neurons in the net will begin to flip to align themselves in this manner, causing the field at other neurons to change, which may cause the original neurons to go right back and flip. And each evolution of the network is guaranteed to decrease the energy of the network. And the energy is lower bounded, the decrements are upper bounded, so the network is guaranteed to converge to a stable state in a finite number of flips. So, is this making sense to everyone? Right. Okay. And that's what we found. Now, where did this energy concept suddenly pop from? Where did I yank it out of? So, this is comes from an analogy to thermodynamic systems, actually ferroelectric systems over here, ferromagnetic systems. Now, in ferromagnetic systems, you have magnetic dipoles, and there's a field through the dipole, and each dipole is trying to align itself with the local magnetic field. So if the dipole is facing this way and the magnetic field is going the other way, the dipole is going to flip. But when the dipole flips, it's going to change the magnetic field at all the other dipoles, causing some of them to flip. And when they flip, this is going to cause the original, this may cause the original dipole to flip all over again. And so if you think of the total field at any current dipole, the field at any dipole is a contribution of the dipole from all the other dipoles. So it's going to be a weighted sum over all the other dipoles of the dipole value times whatever interaction there is. And this interaction is going to be inversely proportional to the square of the distance between the dipoles plus this external term B, which represents the external magnetic field. And so the response of each dipole is simply going to be that it's going to flip to align itself with the local field at each time, if you just look at each dipole individually. And so dipoles will keep flipping. A flipped dipole will change the field at other dipoles, which may change the field at the current dipole, which may flip, and so on. So when does it stop? Again, we can define a Hamiltonian. These are it's physics. You can define something called a Hamiltonian of the system, which is the total energy of the system. And the energy of the system, this is directly from physics. The energy at any particular dipole is going to be the product of the current value of the dipole and the field at that dipole. You sum over all the dipoles. And so the systems, we know that physical systems are always evolving to minimize their local potential energy, right? And so this is basically what. And this, as you can see, is a very strict analogy to what we saw with the Hopfield network. And so you can think of this dipole as always decreasing its energy. So now the state of a dipole of the system is going to be basically the combination of the bit values for all the dipoles. So although there's no real ordering over here, if I were to lay them out, using some hypothetical unrolling against the x-axis, and the energy of the system as the y-axis, the system is going to keep evolving to reduce its energy. And it will eventually stop whenever it hits some local minimum. Now,
wait, will it stop at local minimum or global minimum?
Look, this is how you're going to eventually remember that every flip of a dipole is going to reduce the local energy. So if you get to a system where flipping the dipoles no longer reduces the energy, then it cannot evolve.
Perhaps it can't get out of the...
It can't get out, right? So it actually ends up at a local minimum. Now, this you may have heard of shape memory materials and things like that. So that's basically what it is. If the system is designed for the current configuration to be a local minimum, when you crumple it or do something of that kind and heat it a bit, you let it evolve, and it's actually going to come back and go back into the original minimum energy system, which is why it's going to regain its shape. Yeah.
So using the spin glass analogy, would each one of the peaks then be like a critical point?
Kind of.
You get over that hump that
You go-
changes the entire system globally?
Yeah. So if you go over the hump, you may end up in a completely different configuration, right? And so a Hopfield network is basically a computational analog of an Ising model. And the energy of the Hopfield network is basically a perfect analog of the energy of this Ising model. So the bias over here, which is the equivalent of the external field that may be imposed on the material, and it's like having an extra unit pegged to one. So in my pictures, I won't always explicitly show it, but then you have to assume that it's always there, right? So I just got rid of that bias, and then I can just define the energy in terms of weights. So this network is going to evolve until it arrives at a local minimum in the energy contour. And it so happens that this ends up being what is called a content addressable memory. Have you guys heard of the term content addressable memory? Anybody? So how do you actually address, how do you retrieve a memory from in a computer? If you want to, if you're running a program, if you want to recall something, how is memory usually retrieved in a standard processor? How do you get it? How do you fetch it?
Specifies address.
Mm-hmm.
Specifies address.
You specify the address, right? And then when you specify the address, you're going to get whatever is in the address. Knowing the address tells you nothing about what is at that address. So it's an address-based recall. There's an alternate way where you say, when I'm trying to recall some pattern, I give you some partial information about the pattern. And then it recovers the entire pattern. So this is called content addressable memory. This used to be a big deal. Well, some years ago, they still have many people working on it. Also called associative memory. And so what this means is that there are memory patterns where you can just feed the network or the system with a corrupted version of the memory pattern, and subsequently the system is going to evolve and is going to give you the entire memory. We call the entirety of whatever was supposed to be in the memory, right? So here are some examples. So this was a network where it stores these two patterns, the Chippendale and the Bugs Bunny. But then if you initialize the network with a partially corrupted version of it, and then let the system evolve, the system is actually going to evolve and go back and recall the original pattern. Here was a very nice example that someone put on the web, where they constructed a network into which you could design the weights of the network to store different patterns. In this case, the clown and the penguin, and I think the world. And you can see it just damages the thing. You let it evolve, it recalls the penguin, right? It's very interesting. So this is the world. And you erase it, it's going to recall the entire pattern when it evolves. This goes on, right? So how do you actually computationally implement this evolution? Very simple. You're going to initialize the network with some pattern. And then at each neuron, you're going to check the field at the neuron. And if the field is, and you're going to align the output of the neuron with the sign of the field at the neuron. That's about it, right? And so you can do this sequentially. You can just go through the neurons and loop over them, or you can do this in block using matrix math. The two are going to give you very similar but not identical evolutions. So when will the evolution stop? Because again, this is just evolution, right? I keep going through the neurons. I check the field at each neuron and align its output with the field. This is an evolution that could technically go on forever, but then of course we know that it doesn't. So one simple way to check when to stop is to check the energy of the neuron energy of the network, which we saw was minus 0.5 times the quadratic term that we just saw, which if you work out is simply going to be y transpose wy, where y is the output of the vector of outputs of the neuron, and w represents the weights. And the network will evolve until this energy term doesn't really change anymore. So adding what we just saw so far to our lessons, in a Hopfield network, given an initial configuration, the pattern of neurons will evolve until the energy of the network achieves a local minimum. And the evolution is going to be monotonic in total energy. The dynamics of the Hopfield network mimic a spin glass. The network is symmetric. Now, here's an interesting characteristic. Because the network is going to evolve until it arrives at a local minimum in energy, and the energy is defined as a quadratic, y transpose wy, minus of 0.5 times y transpose wy. So if y is a local minimum, minus y is also a local minimum because both of them have the same energy, because it's a quadratic. Y squared is the same as minus y squared, right? So we're going to have the network being symmetric. If a pattern y is a local minimum, so is minus y. And the network acts as a content addressable memory. If you initialize the network with a somewhat damaged version of a local minimum pattern, it will kind of evolve into that pattern, effectively recalling the correct pattern from a damaged or incomplete version. So I'm assuming all of that was clear. So can we check these statements? This first statement, network activations evolve until the energy of the network arrives at a local minimum. True or false, guys?
True.
Right? And these are a form of content addressable memory? Also true. And is it possible to analytically determine what the memory will be by looking at the weights? I haven't actually explained anything about this, right? But what is your intuition?
True.
It's going to be very complicated, right? Because we said that there can be multiple minima. So it turns out it's actually not feasible. And the reason it's not feasible is very simple. Now, if you look at this guy here, if you look at the energy is a quadratic. How many minima can a quadratic have? Right? If it's convex, it's going to have, if it's concave, it's going to have just one, right? If it's convex, right? So how am I saying that it actually stores multiple memories? I'm saying we claim that it stores multiple memories for a very simple reason. Now remember that if these are my axes, if I have only 2 bits, there are only 4 possible valid values. The quadratic itself might be might be something that has a minimum over here, but there's no way of actually getting to this minimum. Only these corners are valid values. So that immediately gets into this discrete space where analyzing the function and determining where the optimum will be is going to be quite impossible, which is why it's hard to determine just by looking at this at the weight matrix what the optimum is going to be, right? So okay. So far we've seen that it's a content addressable memory. But then how do I actually use it? In order to use it, I must be able to design the network such that it stores specific patterns in memory. And so if this is the case, how many patterns can we store? And how do you retrieve these patterns? Right? So let's see how many patterns we can store. How do you make the network store a specific pattern? Now, how do we make the network store a specific pattern? In order to store any specific pattern, the weights must be such that the pattern has a local minimum in energy at that arrangement of weights, right? So, for example, if I want to teach the network to remember this image, then each pixel over here has a value of +1 or -1, or 1 or 0, depending on how you set it, right? And so if this is say a 64 pixel image, then I'm going to need 1 pixel, 1 neuron per pixel. So my network would have 64 pixels, and there's a specific arrangement of ones and zeros that I want the network to remember. So we have symmetric weights. So if I have n neurons, I have n squared over 2 weights, or more precisely n times n minus 1 over 2 weights. Right? Now, we will also remember that a network that stores any pattern P also stores minus P, because we saw that the energy is symmetric, right? And we also saw that a network can store multiple patterns, because you have this energy contour, and this energy contour can have multiple minima. Now, I want to design my network so that the specific patterns that I want remembered are at these values. So the networks must be designed, the weights must be chosen for such that at the specific patterns, if you flip any one bit of any of the patterns that you're trying to remember, the energy will increase. Or more specifically, for any given pattern, there's no, if you look at the field at every neuron, then the field at every neuron must align with the correct output. So again, the patterns that we can store are going to be points in the corners of a hypercube, because every bit is binary, right? And for every pattern that is stored, there's a negation, which is a ghost pattern, which is also likely to be stored. Now let's look at what happens. The actual operation, if you look at this guy, when I draw it this way, you'll see that in any given evolution, if y is the current output of the neuron of the network, then you multiply this by w, and then you look at sine of w, and this is wy, and this is going to be the new output, right? Now, when is a pattern stable? A pattern is stable if sine of wy equals y, right? Now, or what is the actual operation that happens? Y may be a current pattern. When I multiply this by w, this vector y is going to be rotated and scaled, right? So this multiplication by w will take it to some other place, maybe here or maybe here, right? In which of these two cases will this equation return the same y? I've shown you two cases. In one case, multiplying by w rolled it down. In the other cases, it kept it in the same arctant. In which case will taking the sine of wy return y?
First case. The first case.
The first case, if it stays in the same arctant, right? So in other words, basically, anytime you multiply y by w, it's going to become a new vector. If you zap it back, it's like projecting it onto one of the corners of the hypercube. If it keeps going back to the same corner, then that pattern is stable, right? In the simplest case, I can just say y equals, say, lambda times wy, right? So if I do this, then I know that the pattern comes back to its own space, right? And now, a pattern is stored if sine wy equals y, right? So we want to design a w such that this holds for the patterns that you want to store. Now, a simple solution is to just say that w has this characteristic, right? wy equals some lambda y. So what would y be in this case? It's an eigenvector of w, correct? So for any matrix, if the pattern that you're trying to store is the eigenvector of the matrix, then that pattern is going to be stored. How many eigenvectors can an n cross n matrix have? Anybody? Guys? How many eigenvectors can an n cross n matrix have?
N.
N, thank you, right? So how many patterns can an N neuron network store? N. Exactly. So it turns out that there's a natural restriction. Firstly, if W is symmetric, all the eigenvectors are positive, right? And you can specifically design, and all the eigenvectors are orthogonal. And we are pretty much guaranteed that we can design our Ws to have N patterns which come back to themselves. But then this comes with a limitation, which is this, that a square matrix can have up to N eigenvectors. So we can intentionally store up to N patterns. But there's an issue. If you actually store N patterns, these N patterns are all orthogonal vectors. If I have N orthogonal vectors as my stored patterns, and if the eigenvalues of all of these N patterns are, say, 1, then every other vector in the space can be expressed as a linear combination of these N patterns, right? And so this means that if the eigenvectors of the W matrix are all 1, then every pattern is going to be remembered. Simply because if I just look at any particular vector, I can write it as a linear combination of the patterns that I'm storing. And because these y's span the space, I can just write wy as w times the summation of ai yi, or summation of ai times wi, which is simply going to get back to a times summation over all eigenvalue vectors of ai times lambda I yi, right? That is the characteristic of an eigenvector. And so what this means is that for many patterns, right, any eigenvectors of W which have an eigenvalue of 1, any linear combination of these eigenvectors is also going to be a stored pattern, a remembered pattern. If you start off the network in that pattern, it's going to stay there. And so as a result, it turns out that if you try to store too many patterns, you're going to get you will not only will the network remember those patterns, it's going to remember a whole bunch of other things that you didn't intend to store, which we will call spurious patterns, right? So the fewer memories we store, the less likely you are to have these spurious patterns. And so the bottom line is that with a network of N units, the maximum number of stationary patterns is actually exponential in N. If W is designed so that all of its eigenvalues are 1, every single pattern that you can have is going to be stored. You want to design W such that the eigenvalues are all unique, and only for the patterns that you want does this characteristic y equals sine wy hold. And this is going to be quite impossible. Now, for any specific set of k patterns, if I give you a bunch of k patterns, so long as k is less than n, it's always possible for me to design a network that will remember those k patterns. It doesn't mean that it's not going to remember other patterns. You can have spurious memories, right? And so, and these guys so you can actually end up with many parasitic memories, things that you don't remember. Now, I'm not actually going over this in some detail right now, but this, it turns out, is very analogous to how we ourselves remember stuff. So you might remember that, as you're walking through, you smell something and an entire childhood memory pops up. Or most of the time, you're not really remembering anything, but if I give you a hint or a small pattern of it, the entire thing comes back. So the manner in which human memory works is very analogous to how these Hopfield networks work. And for the same reason, we are also prone to parasitic memories, that you can actually remember stuff that was not true simply because they're in the right subspace. Now, the question is, I have a set of k patterns I want the network to remember. At the same time, the network is going to end up maybe remembering things that it was not intended to remember. So how do I find a network to store a specific set of memories while minimizing the number of spurious memories that it can recall? So going back, designing a network for a specific set of memories means that you have to design the weights such that this energy of the network is minimum for the desired pattern and not a minimum for the other spurious patterns, right? So again, this means that if I write down the energy, which is minus half of y transpose wy, I want this to be minimum or a local minimum at all of the patterns that I'm trying to store. And at all the other patterns, I don't want to store those. So I want to increase the energy at those guys. So if I initiate the network at any of these other patterns, it should sort of evolve and fall into one of the patterns that I am trying to remember, right? Make sense to everybody? Now, how would I do this? Anyone? I have this energy function. I want it to be minimum at a specific set of patterns, and I want it to be maximum at other patterns. How would I do this?
You set, like, try to differentiate, like, minimize it with some constraints.
Thank you, right? So what I can do is, I'm just adding in the bias term just for, just to make it more complete, right? So here is my energy term again. I want to make sure that the energy is minimum at the patterns I'm trying to store. So which means that the sum of the energy at all of my target patterns must be minimized, right? But is that sufficient? Minimizing the energy at the target pattern is good, but what else did we not want, or what else did we want? So you want to maximize the energy at the non-target patterns. And this is going to be your objective function. You minimize the energy at the target patterns, you maximize them at non-target patterns. Does that make sense to everybody? Right? Now, given this, how are you going to solve this? Anyone? Come on, guys. This is the last class. So give me an answer. I've given you an objective. How do you minimize it?
Gradient descent.
Gradient descent. Thank you, right? I can just compute the derivative. And what is the derivative of this one here? If I have E equals minus y transpose wy, what is the derivative of E with respect to y? Anybody? E with respect to w? Anyone remember this? So here, look at this, right? If I give you ax squared, what is dE over dA? Or I'll just call this w. And let's say these were scalars. What is dE over dW? This is simply going to be x squared, right? So that's easy. And now, in the case of vectors, I have y transpose wy. This is what it looks like. Shapes. The derivative with respect to the matrix, what must its size be? It's going to be the same size as the matrix transpose. If it's square, so it's going to be the same size as the matrix itself. So this is going to be y times y transpose. Right. So that's the derivative with a minus sign in front of it. Okay. And so we're going to get that the simple gradient descent is going to be minus y transpose. That's the derivative of E with respect to w. So I'm going to be summing the outer products of all the patterns that I'm trying to store and subtracting the sum of the outer products of all the patterns that I do not want it to remember. And this is the derivative that I would try to minimize, right? Now, what can a problem here be if I want to implement this? Anyone? So let's say I have n neurons in my network. How many patterns are possible with n neurons? N? No, how many total patterns are possible? Right, remember, what are the various combinations of n bits? There's a chalk.
It's on the chair.
Yeah, so if I have n bits, right? Then remember, if I had, for example, 3 qubits, 3 bits, then the possible values are the corners of the 8 corners of a cube. If I have 2 bits, the possible values are the 4 corners of a square, right? If I have n bits, how many possible patterns do I have? 2 raised to n. So that second term over here, how many terms will I be summing over in my derivative? 2 to the n, right? So basically, I'm saying that I want to minimize the outer products, sum of the outer products for all the patterns that I want to remember. And I want to maximize the sum of the outer products for all the patterns that I don't want to remember. But the second term is going to be summing over an impossibly large number of values. And so this is computationally infeasible. It's not going to be possible, right? So what is the solution? By the way, so once I begin looking at this first term, if there are different memories that I want to remember, I can increase the importance of any particular memory by just repeating it. So you can think of this first term as having samples being drawn from the distribution of memories that you want to remember. Things which are drawn more frequently are going to be more memorable. Things which are drawn less frequently are going to be less memorable, right? And so more repetitions is greater emphasis. And these guys, they're going to be an exponential number of them. So the question we ask ourselves is, do I really need to include all exponential numbers of terms in order to actually perform my gradient descent? And so let's look at this again. This figure over here is just showing an illustration of the energy contour. The x-axis represents states. Although I've drawn it continuously, you have to remember that each point basically represents some point, some state. It's 1 of 2 raised to n possible states, right? And the y-axis represents the energy. And we want the weights to be designed such that the energy of the system is minimum at the patterns that we're trying to remember. So if you just initialize the weights any odd half, then you're going to have some energy contour. Now, there are some patterns that you would like to remember, which are shown here in yellow. So you want to modify the weights so that the energy at these patterns is pulled down. At the same time, these are the target patterns that you're trying to remember. At the same time, you want to modify the weights such that the energy at every other pattern is pulled up. And those blue arrows are going to be exponential in number. The number of yellow arrows is going to be much smaller. So if I draw the figure, it immediately becomes apparent. It's not necessary for me to pull up the energy everywhere. For every target pattern, if I pull down the energy at the target pattern and only pull up the energy at the valley adjacent to it, then the target pattern is still going to become memorable, right? So this means that I don't need to consider all exponential number of these patterns. For each target pattern, I can find the nearest valley, and then I can try to pull down the energy at the target pattern, pull up the energy at the valley. How would I find this valley? Anybody? Gradient descent? Why? No, see, what happens when I let the network evolve? What happens to the energy? When the network evolves, it's going to keep changing state, right? As the network evolves, remember the figure I showed earlier? The ball is going to roll down into the local valley. And so all I need to do is to initialize the network at my target patterns. Then let the network evolve. When it stops evolving, it's going to be at the local value, right? And so the solution is very simple. Here's what we will do. I'm going to initialize my W, and then I'm going to compute the outer product for all of my target patterns. Then I initialize the network at each of my target patterns, let it evolve. When it settles, that term is going to be used in the second term. So over here, this first term is going to be computed over all of my target patterns. This second term over here is going to be computed over all of the patterns that the network settles in when it evolves, right? Okay. And then you update the weights. So, or I could do the SGD version of it, where I can randomly pull up one of my target patterns, let the network evolve, and then just use the difference between the outer product of the target pattern and the value that it settles at. And this is going to be used for my update rule, which is much simpler, right? And I keep doing this till the entire energy of the network converges, right? So now, but then even this simple technique, we can actually begin looking at a few things, right? First, do I need to, actually, I'm taking one more step over here. If I want to consider all valleys, then I'd actually have to randomly sample I'd have to restart the evolution at each time to get to the valley. But then if you're really only interested in valleys close to patterns that you're trying to store. So valleys that are far away, we don't really worry about those because they're probably not things you want to remember and you're unlikely to encounter. Okay, anyways. So here's a possible problem. If I just start the network at some target pattern and let it evolve, then there may be another pattern. So when it evolves, it's going to stop at some pattern, stop at some valley, and it's going to pull it up, right? But there may be another pattern downstream along the same valley. So when I'm performing SGD and I'm starting with one of my patterns and letting the network evolve, and I go to the local valley and then I pull it up, in the process, I may actually end up pulling up a pattern that I'm actually trying to store, right? So how do we avoid this? How do we make sure that you're only pulling down the pattern that you want, the energy for the pattern that you're trying to store, and not inadvertently pulling up the energy at other patterns? Now, especially if you have a large number of patterns, you can't actually run a test and say, okay, I'm minimizing the energy here. Am I somehow inadvertently pulling up the energy at a target pattern? You can't really say this. What you can do is this. You can decide what is the minimum gap between any two patterns that you're trying to store. And so these are just bit patterns. You can have a gap, right? And so if I have the minimum gap, so let's say I have two patterns and say these things differ in 4 bits, then I know that if from any place I evolve no more than 2 steps, I'm not going to get close. I'm not going to go so far that I actually wander into the next pattern. So this means that I don't actually let the network evolve all the way till it hits a valley. I only let the network evolve a few steps. And so this is a solution over here to avoid something of this kind. And the problem with, just letting it evolve is that the pattern it pulls up may be something that's actually well stored at this point. It's actually pretty close to the valley, right? So we observe that this is related to the same idea that you don't need to raise the entire surface, energy surface. In order to store any particular pattern, it's sufficient for the energy contour to be a local valley in the vicinity of that pattern. So you don't care what happens out here. You just want the energy to be energy contour to be a local valley at the pattern that you're trying to remember, right? So you can decide what is the width of this valley to be. How many errors will you tolerate when you're trying to actually recall the pattern? And so based on that, you just raise the neighborhood of each target memory by letting the network evolve for only a few steps from the pattern that you're trying to remember. So folks on quiz, can you please mute yourselves? Folks on Zoom, can you please mute yourselves? Right. So at each target pattern, you can just let the network evolve only a few steps rather than trying to let it evolve all the way to convergence, right? And so the idea is you're going to do something like this. During each SGD step, you would initialize the network somewhere, and then in each step you pull up one of your target patterns, and then you let the network evolve a finite number of steps. The number of steps you let it evolve is the width of the valley that you want that pattern to be in. And then the actual correction that you will use is going to be wherever the network ends up after those many steps. And so it's going to be the difference between the outer products of the target pattern and the pattern that you end up on after the given number of steps. Again, the whole thing is very intuitive. There's a lot of math, and if you look through the papers, it's going to be very confounding if you actually read it. But then if you just look at the pictures and think through it, even my slides are more confusing than they need to be. So a Hopfield network, to summarize, with n neurons can store up to n random patterns. It comes with many parasitic memories. Networks that store order of n memories can be trained through optimization by minimizing the energy of the target patterns while increasing the energy of the neighboring patterns using simple gradient descent. So very simple, right? Now, so far so good. Any questions? There's nothing particularly complicated about these networks. It's very easy to analyze, as you just saw, right? But then it comes with a restriction. And the restriction is that if I have a neuron network with n neurons, the number of patterns I can actually store is significantly less than n if I want these to be sufficiently memorable. In the upper limit, it's going to be n, right? So how do I create a network that can actually store more than n patterns? Now remember that storing no more than n patterns is a physical limitation, right? That's how many eigenvectors the weight matrix has. And yet my claim is that it's possible to manipulate these networks to store more than n patterns. So if I were to ask you how you would do it, how would you do it? Anybody?
Add more weight.
Add? The number of weights is fixed by the number of neurons, right? Anyone? Yeah.
Just remove the restriction that each neuron has to be like an eigenvector and try to be like that.
But that's just the math, right? You can't have more than n eigenvectors for the weight matrix, period.
Linear combinations of n. Linear combinations of n.
It's still going to be, you still end up with the same linear restriction. Anybody else?
The symmetricity?
It's still a square weight matrix. The number of eigenvectors is going to be the same. Anyone? So this is where the really creative bit comes in. You can thank Hinton for it. I'm going to take my n neurons and I'm going to patch a whole bunch of don't care neurons, don't care bits. I'm going to take my n bit patterns And I say in addition to these n bits, there are these large numbers of a number of extra bits whose value I don't really care about. And so you can, so you add a large number of neurons whose values are irrelevant to you. So now if I add an extra k bits, my network is going to end up with k extra neurons because I have 1 neuron per bit. And now the capacity is n plus k as opposed to n. And you're still interested in n-bit patterns. So the way you can think about it is you have what are called, let me see if I have the picture here. You have what we call visible neurons. These are the neurons which store the patterns that you're interested in. And then what we will call the hidden neurons, these are the neurons which store all the other bits that you don't really care about. And this can be anything, right? So for example, if this is a pattern that I'm trying to store, what I will do is augment it with a whole bunch of other bits. And now I get this much, much larger pattern. But I don't really care about the remaining k bits. I can set it to any odd thing. And now I get this n plus k bit pattern. And now I can build a network that can store n plus k patterns. And now this is beautiful because I can store n plus k patterns, but I'm only going to read the first 10 bits. And the capacity of the network has increased. But then this naturally comes up with a question, what must these, so these are the visible bits, and these are the hidden bits. They're the don't care bits, but I'll call them hidden bits. Another question becomes, how do you set them? What values must these don't care bits actually take? And so there's a couple of different options. I can just fill those guys randomly, or I can optimize. And then once again, how do I optimize? Standard optimization methods should work. But then there's also this other question, right? If I'm trying to recall something in memory, how do I recall it? So if I recall it, then I can do this using the standard evolution mechanism, but then there's something that we're not taking advantage of. And what we are not taking advantage of is this, that we don't care about errors in the gray bits. So if you can actually take advantage of this fact to have better recall of the colored bits. That make sense? Right. And so making errors in the don't care bits doesn't matter. So there are different ways of figuring out what these don't care bits must be. You can have simple random setting of these don't care bits. And you can have the usual training and recall strategies for Hopfield nets, but it doesn't sufficiently exploit the redundancy of the don't care bits. And now here's the other thing that we can take advantage of, that if for some pattern is more important than the other patterns, then because we're actually creating these augmented patterns by patching a whole bunch of don't care bits to the pattern, I can create multiple of these. So for example, if I have something like plus 1, minus 1, and I'm trying to remember this, then I can create minus 1, plus 1, plus 1, plus 1 as one pattern. I can create plus 1, minus 1, and minus 1, plus 1, minus 1 as a second pattern. And both of these patterns, these are the visible patterns bits, these are the hidden bits. I have 2 copies of the same visible pattern with different values for the hidden pattern. Then I can try to store both, which means that this particular pattern becomes more memorable, easier to remember, right? So these are all options that we can consider when we begin to exploit these hidden neurons. But now, how many such patterns do you want to store? For any given visible pattern, how many different augmented patterns do you want to store? We don't really want to explicitly consider this. We want to let the network decide. And so the way we do it is by treating the whole thing as a probabilistic model. And this takes us into Boltzmann machines. So this is what a Boltzmann machine really is. And the idea is this. We are defining the energy of the network, and you're always minimizing the energy of the network. Minimizing the energy of the network is also strictly equivalent to maximizing or when the network evolves, you're choosing the Y, which has the lowest energy. This can also be thought of choosing the Y, which has the maximum probability if the probability distribution itself is defined as e raised to minus of the energy, which means that when you minimize the energy, you're maximizing the probability because these two are monotonically defined, related. If E goes down, P goes up. And then once you think of it in this term, that the probability of any pattern is proportional to e raised to the negative energy of that pattern, then now you have converted the whole thing into a probabilistic machine where you're trying to select the pattern that has the highest probability. And this particular probability distribution is what is called the Boltzmann distribution. Now, how we arrive at it is on the slides. I'm not going to go over it. But then, once again, this is what the Boltzmann distribution is going to look like. You're going to say, because the probabilities must all sum to 1, right? And so I can define the energy of the network for any given pattern, exactly as I showed before. S here represents the bits. It's minus of summation over all pairs of bits of the weighted product of the bits plus the bias term. And the probability of any bit is simply going to be, any pattern is simply going to be e raised to the negative energy of that pattern normalized. The denominator term is a normalization term, which makes sure that the probabilities of all the patterns sums to 1. And then once you do this, we can actually convert, and once you make it a probability distribution, then your neurons can no longer be deterministic because the whole thing is a probability distribution. The entire system is stochastic. And because the neurons are stochastic, they have some entropy. And so you can think of the whole thing like this. Instead of just having this very deterministic behavior where every neuron considered its own field and flipped its sign to align itself with the field, you can now add a little bit of noise and say that every neuron considers its own field and it's going to flip its sign to align itself with the field with some probability. And so if that happens, then the network is still going to evolve, and it's going to evolve and it's going to arrive at some stable configurations. And so if you look at the network, eventually after a lot of evolution, it's going to arrive at a probability distribution over the states, and this is what is called the Boltzmann distribution for the network. The equilibrium probability distribution is the Boltzmann distribution of the network. Anyway, these are just definitions. Going back, this is a stochastic Hopfield network because we've converted the whole thing to be probabilistic. And a stochastic Hopfield network is a probability distribution over states, where a state is a binary string, a pattern, and it models a Boltzmann distribution. The parameters of the model are the weights of the network. And the probability that the network will be in any state is given by P of S. It's also a generative model. You can use it to generate patterns. And how does it evolve? I'll skip the math, but here's how it evolves. Earlier, every neuron just considered its local field and flipped itself to align itself with the local field. Now, if you work through the math, you would find that the neuron behaves slightly differently. At each neuron, the neuron computes a logistic, a softmax over the field. So it's going to be the sigmoid, the logistic softmax, sigmoid, they're all the same thing, right? So the probability that any neuron takes the value 1 is going to be the sigmoid function applied to the field of the neuron, field at the neuron. And so if you ever wondered where the sigmoid came from in neural networks, if you just go through the slides, you will see how it is actually arrived at. This goes back to Hinton's original work on Boltzmann machines back in the 80s, where this is just a natural outcome of the manner in which these Boltzmann machines evolve. But the point is this, that each neuron is simply going to consider, look at the local field. Every neuron over here is going to look at the local field. And the probability that it's going to take a value 1 is obtained by putting the field through a sigmoid. You can think of having a coin whose probability of heads is given by the sigmoid. The neuron flips the coin. If it comes up heads, it takes the value 1, otherwise it goes to 0. Now, again, the evolution is exactly the same as before, right? So here's how the neuron would evolve. You initialize the neurons, and you'd cycle through the neurons and randomly set them to +1 or -1 according to this probability at each neuron, right? And there were different sampling strategies. You can come up with your own. And you just keep cycling through the neurons. Now, there's a stochastic aspect to it because neurons are not deterministically flipping. At each point, they're flipping a coin, right? So how does this network evolve? It turns out that if you let it evolve for a very long time, and if you do this many times, right, eventually it's going to be visiting only it's going to be visiting all probable states with some probability. And the probability distribution of visiting any with which it visits any state is the Boltzmann distribution. But the patterns that you want remembered and recalled, they are going to be expected values, expectations over this Boltzmann distribution. And so the actual technique is going to be for the evolution of the network is going to be something like this. You'd initialize the network with some initial pattern. Then at each neuron, you're going to compute the sigmoid on its field and flip a coin according to this probability to set its value. And this continues for a long time. And eventually, you have to stop when it arrives at a high probability configuration. But then again, what do we mean by high probability configuration? You get into fuzzy areas. So the actual computational process is this. You let the network evolve, and after a long time, you take the last few steps of the evolution, and then you average them out, average the states out over the last few steps of the evolution, and just take the signs of the bits. And that's going to give you a stable state. So it's just a minor modification to how the standard Hopfield network evolves. And we can still use this network for all the things that we saw, right? I can use this for noise reduction. So I could start off with a pattern which has a lot of noise, let it evolve. Then when it actually converges, it's going to give you the final pattern. Or I can give you a partial pattern, let it evolve. And it's going to fill out the pattern. We saw a couple of different examples of this, right? Now, how would you train such a network? It turns out that once you define it as a probability distribution, then training becomes a maximum likelihood process, but then completely ignoring all of the probabilistic interpretations. We can still arrive at something that's very intuitive, which goes all the way back to Hopfield networks. So when we were working with Hopfield networks, what we did to train the network for any pattern was this. We had some energy contour. We initialized the network at whatever pattern we were trying to remember. We let the network evolve a few steps. It arrived at some other pattern. And so this was the pattern you were trying to remember. This was the pattern you were not trying to remember. You took yp transpose minus y bar transpose. This was the gradient that you adjusted the parameters by, right? Except now we have this issue that we don't really know the pattern. So we do something very interesting. We're going to try to construct these patterns. So observe that we actually have these patterns that we are trying to store, but then the pattern has visible bits and hidden bits. So this might be some pattern that you're trying to store, and then you have all of these guys that you do not know. You don't know what it's supposed to be. And so we do not know how to fill those guys. We are going to optimize the process of filling those guys. So what we would do is to initialize the network, fix these visible bits, and let the network evolve so that only these things change without ever letting these bits be modified. And that's going to be the completed pattern that we use over here. So even finding this pattern is going to be done through optimization, where you initialize the network you initialize the visible bits with the pattern that you want to store, and let the rest of the bits evolve. And when that converges, you're going to get the completed pattern. That's what you would store. And then, subsequently, in order to get here, at this point, you might have got some completed pattern, which you got through evolution. You're going to initialize the network now with this completed pattern and let it evolve, at which point all of the bits are likely to change. And that's going to give you the second pattern. And the difference between these two outer products will be the derivative with which you would update the network. So again, there's a lot of mathematical symbolism over here on the slides, but the basic idea is just this. The gradient update rule is this one over here. It's the difference between the outer products of the pattern that you're trying to store and the pattern that the network evolves to from the pattern that you're trying to store. But then the pattern that you're trying to store is itself partially unknown. So there are two steps to the process. First, you initialize the network with the portions of the patterns that you do know, let it evolve, and find out what this guy must be. So that would be your pattern that you're trying to store. Then you initialize the network with this entire pattern and let it evolve for a few steps. And that's going to be the pattern that you do not want to remember. This is the downstream pattern. And so that's going to be the second guy over here. And this is the overall gradient that you would use in your gradient descent. Now, in order to arrive at this very simple algorithm, there's been a lot of math that you can actually look at that has been written about the stochastic interpretation of Hopfield networks and Boltzmann machines and such like. But at the end of the day, it just comes down to this. It's a very simple Hopfield network where you even optimize the patterns, the hidden portions of the patterns, to decide what you must remember, right? So we call it simulations, and that's going to be the gradient. So the overall training for the network looks like this. You initialize the weights, and you clamp this. They call it clamping. You fix these bits, clamp these bits, let it evolve to compute these bits. That's going to get a complete pattern. That's the first step. Then you initialize the network with the completed pattern, let it evolve a bit more. You're going to get the second term, and the difference between the two outer products is going to be the gradient that you're actually going to be updating your network. So this general principle of augmenting patterns that you're trying to store and treating the whole thing as a probabilistic machine is what was called a Boltzmann machine. And Boltzmann machines were proposed. It's a lot of complication for not much gain, in my opinion, over the basic Hopfield network concept itself, because Hopfield networks by itself are very easy to understand and interpret. But these things have been were probably the first attempt at using neural networks as generative models. because it turns out that now if I actually train the network and think of this as a probabilistic machine, then I have learned a Boltzmann distribution, and then I can draw samples from this Boltzmann distribution by just randomly initializing the network and letting it evolve in a stochastic manner. Now there are extensions to the basic Boltzmann machine where called the restricted Boltzmann machine, where you don't let the hidden values talk to one another and the visible values talk to one another, because it makes the computation much simpler. And much of the math that has followed has actually been about restricted Boltzmann machine, also called, I think, the harmonium model by Paul Smolensky, who first invented them. But what are things we can use them for? You can use these things for denoising. If the machine has been trained to remember some patterns, if you give it a noisy version of the pattern, it's going to evolve out of it. You can use it for completion. I can give it a partial pattern, and it's going to recall the entire pattern. You can also use it for classification. So this is the beautiful bit. And the way you would use it for classification is that these hidden values, I can actually say that my pattern has my features, and these could be my class label. My class label itself can be represented as a binary pattern, one hot or anything else. And then these would be my hidden bits. And once you use this to train, to maximize the likelihood of all of your training data, basically try to make all of the training data memorable. Then subsequently, when you're trying to perform classification, you'd only present these bits and let the entire network evolve, and then you'd read these bits to decide what the class is. And so it also can be used for classification. Anyway, I'll stop right here. It's 9:20. Thank you for your patience. Thanks for coming to this last class. And you, of course, have seen all the posts about the projects and such like. Good luck with everything in the future.